Now, we have said we have taken three cases. L is equal to 3 meter, L is equal to 10 meter, and L is equal to 30 meters. And we looked at how the load versus moment curve is going to change. Now, whether to distinguish the column as short column or long column, the definition is to use effective length. In this case, the previous case, what we considered was a clear hinged case, which is prevented from moving laterally. So then your effective length is equal to the clear length of the column between the supports. It was easy for us to calculate effectively. But most of the time, we will not have this kind of clear boundary conditions. So the column top and bottom, depending upon how the members are connecting at the joint, you can have a close to hinged condition, or you can have a close to fixed condition, or it will be most of the time it will be in between. So in that scenario, how to consider or calculate effective length? So let's see what is the definition of an effective length. So the effective length of a column in a given plane may be defined as the distance between the points of inflection in the buckled configuration of column in that plane. So that means when the column is going to buckle, right, then you are looking at as the distance between the points of inflection. So what is the meaning of point of inflection? The curvature of the column is changing from, slope is changing from positive to negative or negative to positive. Those points are called as points of inflection. Okay. Or in other words, so LE will become K into L, where K is your effective length factor and L is your unsupported length. Now let's say what is unsupported length. So unsupported length here is basically L. That is what is given here. Right. Now code, our IS code, class 25.13 defines the unsupported length explicitly for various types of constructions. Okay. So for a cast in place construction or even for precast, most of the time in buildings we use framed construction. L here is taken as the clear distance between the floor and the shallower beam framing into the columns in each direction. That means you can have L, because the shallower beam means for a particular column, the left and right side of the column, you can have beams with different depth also, right? So in that case, what you do is you take a larger length, unsupported length, not the shorter length. So that is the way it is saying that as a shallower beam. When you take shallower beam, as a clear distance between the floor, top surface of the floor, and the shallower beam, then you end up with more L. Okay, that is class 25.13. Now, again, we talked about it in the beginning of this module. The unsupported length in one direction may be different from that in the perpendicular direction. Or, in other words, a particular column can be a short column in one direction and it can be a slender column in the other direction also. So, for a rectangular column section with a width of dy and a depth of dx, the definition LEX is KX times LX, and similarly LEY is KY times LY are used to denote effective length. So, or in other words, you have to calculate effective length about both axes. So, the K factor can be different for two directions for the column that what we are considering. Now, let us look at this one example that we have shown. So, I have taken this simple typical plan, which is having a grid of, let's say, in the x direction, three bays with 6 meter length. Total width is 18 meter, and then you have on the y direction you have 4 into 3 bays at each spacing of 4 meters. So you get 12 meters. And the beams have dimensions of 300 by 450 and columns with 300 by 300. And beams are actually in one direction. I have in the longer directions, I am taking a dimensions of 300 mm by 600 mm. So if I take one particular column, let's say this, now I have beams that are running along this direction and beams that are running along this direction. So now let's say I am looking at this beam column towards this direction. So you can see here in this case, right? So you can clearly see here these beams are, now what we are looking at is this is the beam, which is, what are the dimension of this beam for the plan that we have considered? It is actually 300 by 450. Okay, because we are looking for this particular column in this direction, right? So similarly, what will be the perpendicular beam to this? This is going to have a dimension of 300 by 600 mm, right? So, and this beam, when you look at it in the x direction, so in this again for this column, in this case, dx is also 300, dy is also 300 because it is a square column. But you can have different directions also, right? So for this column, then what would happen to this? Let's say this is a let's say clear height of, let's say you have for clear height of, let's say 3500. Okay, so then what would be Lx? L is equal to, let's say if I take uh, in this case, what is that Lx that what we are saying? Let's say um, so you are measuring from the top surface to the shallower beam. So this would be the length of your x, which is bending about x-axis. Okay, so in this case, you are taking this as Lx. Similarly, Ly will be from here to here. Okay, which is going to be about bending about the y-axis. Okay, so because this is your x-axis bending and this is your y-axis bending, right? So you can calculate slenderness ratios kx times Lx by dx and ky times Ly by dy. So you have to look at. So the point what I'm trying to tell here is the column is part of moment resisting frame that is coming both x direction as well as y direction. So you have to look at what is the axis about which you are considering the slenderness ratio. So appropriately, you have to choose the unsupported lengths to calculate your slenderness ratios, right? So in this case, we have talked about this. When you look at this case, now again this column is part of both the frames, frame which is part of the x direction and frame that is, so this column actually a part of this frame. Similarly, this is also part of this frame. Okay, so we have to appropriately calculate the dimensions. Okay, so you have to consider that. Now, so okay, so we have said okay how to calculate your unsupported length. Now let us see what is the implications. Okay, uh, effect how the effective length is going to be different when you have different boundary conditions. Now, first case, what I am saying is a column which is braced or non-sway frame. So, what is the definition of a braced or non-sway frame is, if I consider the bottom and top, they are not moving relative to each other. So, there is no lateral sway that is happening. Or in other words, this point is not moving like this. It is going to be always the top and bottom ends of the column are not going to move relative to each other. They are going to stay as it is. Okay, so though they are staying at each with respect to each other same directions, now I can have different boundary conditions. So what I am considering here is the top and bottom are rotationally fixed. That means I am not allowing any rotation. Of course, these supports are not free to move laterally. So that means the displacement at these 2 points are also zero, and the rotation also they cannot rotate. So it's a fixed condition, and they are also laterally restrained to move away from each other. They are also called as non-sway frame because they are not allowed to sway. So braced or non-sway frame are one and the same. Okay, so when you look at this deformed configuration for this particular beam, so then you will find that you get this kind of deformed shape. You have a zero slope and then it goes like this and then comes and comes like this. So you will find that this is the location at which it is changing its slope, right? So you will find that the effective length will be equal to half of your clear unsupposed length of the column. So it is going to be 50% of your length of your column for a both ends rotationally fixed. Now let's look at another case. One end is fixed. Okay, that means it cannot move and it cannot also rotate. But the other end, you'll find that again that end is restrained to move laterally. However, it can rotate. So For this case, if you see, my point of inflection, of course, is the hinge point will be here, and at this point it will be here. So our definition for effective length is it is the distance between the points of inflection. So you will work out this to be 0.7 L. Okay. So as you can see, if I am relaxing the boundary condition from fixed to one end pinned, now what happens to the effective length? The effective length has increased from 0.5 L to 0.7 L. Now let's look at the next case. Now I'm relaxing it further. Now instead of having pinned at only one end, if I am making the boundary condition as pinned at both ends, however, both of them are restrained. Okay, they cannot move with respect to each other, displace with respect to each other, but these joints can only rotate. Now, when these conditions happens, the effective length will become basically equal to L. So that is the condition that we saw in the previous definitions of short columns, moderately slender column and very slender column. Because hinge, then effective length is equal to your unsupported length, which is your L. Now you can, this is a more practical case. Okay, this is a practical case. Okay, where this pin, fixed are a theoretical considerations, but in reality, your joints will be neither pinned or nor fixed. It will be somewhat in between. That fixity you have to determine based on the relative stiffnesses of the members that are connecting in the joint. Now, if you look at it, so the joint is going to somewhat rotate like this. So you will find that this point of inflections is going to be somewhere in between, or in other words, it is going to be K value is going to be between the fixed condition and pin condition. So depending upon what kind of fixity that you have at the top and bottom of the column, K value can be either 0.5 or can be 1. Again, you have to keep in mind that these two columns are not free to sway. They have been restrained from sway, or in other words, they are not moving with respect to each other. They are only rotating. There is no lateral sway that is happening. So this is the condition for a braced or non-sway condition. So in this case, if you look at it, what is the maximum value of K that is possible? Which is 1. What is the minimum value of K that is possible? Which is 0.5. So for a braced frame, the effective length factor K is going to be between 0.5 and 1. So the moment you find that the column is part of the braced frame, then you can fix that K is going to be between 0.5 and 1. Now let's look at the next case, which is an unbraced or a sway frame. So as the name indicates, now the top and bottom portions or bottom points of the column are free to move with respect to each other. So this is the case. So now what we are considering is, again we are going back and looking at both the ends are rotationally fixed. Okay, so it's very clear. It's rotationally fixed. Okay, so rotationally fixed means, again you see here, this is fixed, but the top point I am putting it on a guided roller. That means this top of the column can actually move laterally. However, the rotation is arrested. So that is why here we have put that as a guided roller. So for this case, if you look at the deformed configuration, it is actually going to be like this. Go like this, going to come like this and this. So my point of inflection is going to be somewhere here, and then I have to extend this outside this, then this is your effective length, which will work out to be equal to L. So you see here, for a fixed case, which is on a one end is on a guided roller, however the rotation is arrested, however it is free to move laterally. For a sway condition, you will find that the effective length for even for a fixed case, it is working out to be equal to L. Now next case is one end is fixed, the other end is free. Basically, one end is rotationally fixed and other is free. So you see here again you have a hinge here. Okay, the other one it's free to rotate, but this is actually fixed support. So if you look at this again, you have to extend it. Then your point of inflection is here and here. and effective length has become now 2 times your unsupported length. So one end is fixed, other end is pinned, but the pinned end is free to move laterally. Such kind of boundary condition, you find that effective length is equal to 2 times unsupported length. So it is increasing, right? The next case is a both ends are rotationally free. So it's basically like a stick, okay, and it can rotate like this. You will find that there is no point of inflection because it is straight, okay, as a rigid body it is moving like this, okay. So it is actually an unstable configuration. You end up with effective length of infinity. So it's a very unstable configuration. Imagine like a pin, like a small stick, and it is one end is free to move and it will keep rotating, right? So, and also there is no bending that is happening on the along the length of the member. It is straight. So that is why there is no point of inflection. So it is going to have effective length equal to infinity, which is a theoretical consideration. You cannot have this kind of a boundary condition. The structure will become unstable. Now, the last case is a more practical case where both the ends are partially restrained for rotation. So that means the rotation is allowed depending upon the fixity of the members that are coming in the joint. You will have some rotations, but then you will find that if you draw again the deformed configuration, you will find that the k values get going to be between 1 and infinity. So for an unbraced or sphere frame, if you look at what is the minimum value k that we are getting, it is 1, which is for this case, okay, which is for this case, which is both ends are rotationally fixed. What is the maximum value that we are getting for k, which is infinity, which is for when both ends are rotationally free. For a practical case, it is going to be 1 and infinity, but you will not have infinity, but we take a maximum value of k equal to 10. Okay? Even if I am doing this somewhat pin to pin condition, I can take k is equal to 10. The moment k becomes 10, your column will, same column, 3-meter column unsupported length will become, now effective length will become 10 times 3, which is 30 meters. Okay. Then designing of such columns will become very uneconomical. I need to put huge amounts of steel reinforcement to account for additional bending moments, which we will talk about it in the next part. Okay. Now, these are all theoretical consideration. Now, how is the code saying, okay, the code wants to be, again, conservatively estimate the demand that is coming. So, theoretically, if you are getting one effective length, what would the code would do? Code would slightly amplify it and give you the values. Okay, that is what it is happening. You see here, if you look at your table 28, the code specifies theoretical value is 0.5. So the code is saying don't take 0.5, slightly amplify it, and you take 0.65. Now, again, the next case, effectively held in position at both ends. So these are basically, these are all restrained. Okay, these are non-sway conditions. Okay, these are all for non-sway. Okay, these are for non-sway. You can see you get 0.7, one end fixed, another end is hinged. You get 0.7 theoretically. Code is asking you to take 0.8 here. Now, both the ends are pinned. We get theoretically 1L. And anyway, this is a very clean case. So, code is saying that you can take 1L only. Now, when you are going for a sway condition or a unbraced condition, you find that fixed, you get 1L for theoretical. Code is asking you to take 1.2L. One end is fixed, another end is free, theoretically 2, and this is also 2L that is specified. Okay, so so these are for sway conditions. So code is giving you anyway. Pinned is theoretically you will have effective length of or k factor of infinity, and it will be highly unstable configuration. We should not design for such cases. Right. Now the big question is, okay, the effective length depends upon whether the column is part of a sway frame or a non-sway frame. Now, how to do that, distinguish that? Okay, so you can see here the structural frames. So the definition of sway and non-sway frame is illustrated here. And the structural frames whose joins are restrained against lateral displacement by attachment to rigid elements or bracing are called braced or non-sway frame. So in this case, you can see that you have a huge shear wall. Okay, this is a moment resting frame. Okay, now in this moment resting frame, at one end, what I'm doing, I'm attaching a shear wall. So the shear wall is going to have a huge rigidity and it will not let the frame to sway. Even if it is swaying, the sway will be very, very small and it will be not very high value. Okay. Now, if I'm not having shear wall in my construction, which is part of this moment resisting frame, or if I do not have adequate shear walls, then you may end up with a lateral sway that will increase your effective length of the column under consideration. So, if a structural frame is not attached to an effective bracing element, but it depends upon the bending stiffness of the columns and girders to provide lateral distance, it is termed as unbraced or sway frame. Okay, so this is the what that we are seeing here. So, this is a simple uh, two-story, two-portal frame, moment resting frame. If you look at it, it doesn't have any shear wall. So when you have a lateral force that is acting due to the shear, you will have this kind of deflection, and you will have a delta for each flow. Though all the beams, everything is connected rigidly by your diaphragm action, still the frame will move. Okay, so that movement is basically your lateral swing. So such kind of scenario we consider that as an unraised or a sway frame. Okay, now how to estimate this quantitatively? Okay, so you can say, okay, let's say you have a shear wall, predominantly you'll have a braced or non-sway frame condition. If you don't have shear wall, this. But even if I'm proportioning my columns and beams adequately, even without shear wall, I can have a braced condition. So, how to quantify that is the next thing, which we quantify whether the particular frame is a braced frame or an unbraced frame by something called stability index. Let's see what is stability index. So, stability index for a particular frame, which is considered for a particular story, we take the free body diagram of a moment resting frame for one particular story, and then the stability index we calculate by a summation of all the axial force that is coming on this particular story. And then if somehow I am able to calculate this delta naught by VU, which we call that as lateral flexibility. Okay, lateral flexibility. So let's say how we get this. Okay, so this delta naught by V is your lateral flexibility. So the stability index is nothing but summation of axial force divided by the story height of the column multiplied by lateral flexibility, which is delta naught by VU. Okay, so if this value, if I am able to calculate, if that Q value, if it is less than 0.05, then we call them as, because this delta naught by V is less than certain value, means it is having less lateral flexibility or it is more rigid, so it is not going to sway. So then we call such kind of particular frame as a non-sway frame. And if Q value is going to be more than 0.05, then we call that as sway or unbraced frame. Now, what is again, the summation of PU is the total vertical load that is acting on the story, and VU is the total story shear in the story that is under consideration, and LC is the length of the column measured from center to center of the joints, and delta naught is the first order relative deflection between the top and bottom of the story. So, it's a first order analysis, or in other words, we are not considering the geometric nonlinearity, and we are calculating the delta naught in the undeformed configuration, and that is your first order deflection value, and that you calculate. Okay, so by plugging into this, it is giving an idea what is the value of a stability index. Higher the stability index, more you are going towards sway condition. Lesser the stability index, you are basically going towards non-sway or a braced condition. So okay, again you see the determining whether the column is part of the braced or unbraced frame makes a lot of difference, because your effective length will highly depends upon whether the column is part of the braced frame or a unbraced frame. So it is very essential to exactly know whether the column is part of a sway frame or non-sway frame. Now let's look at this one example. So I've taken a simple free body diagram of one particular story. Okay, let's say that I've done the first order analysis by any method, and I'm giving you that value delta naught. Okay, and I'm also giving you what are the shear that is acting on all the columns. Okay, for example, here first column 40 kilonewton, second column 60 kilonewton, third column is a 30 kilonewton. So when you do lateral load analysis, again, depending upon the stiffnesses of the columns, we can each story shear can be assigned in proportion to their lateral stiffness like this. Okay, and I've also done analysis, and I'm giving you this load as each column is 1000 for an interior column 1500. The rightmost column, I'm saying that it is going to have 900 kilonewton. Now all these columns are also connected by the slabs, so everything is going to move laterally by the same magnitude. So for all the columns, it is going to move by delta naught only. Okay, they are all connected by rigid slabs. Okay, so if I give you this value delta naught as 12.2, so now let us see what is Q that we're getting. Now, what is the definition of Q? Summation of PU. So, what are the total summation of axial force that is coming? 1000, 1500, 900. So, I add all of them times delta naught by VU, total shear story that it is acting. So, what is delta naught? Which is 12.2 millimeter divided by summation of all the story shear. Story shear means all the shear that is resisted by the column. So, that's going to be 40 plus 60 plus 30. So, that is this. And the height of the column is 3 meters, which is 3000. So, when you do that, you find that Q value for this case is 0.1063, which is larger than 0.05. So the frame is unbraced or it is swaying. The amount of sway is quite significant. So you need to consider this frame as an unbraced frame. So you will find that this largely depends upon your delta naught by VU, okay, which is your lateral flexibility. So if somehow I am able to calculate this delta naught by VU or a lateral flexibility based on the dimensions of the columns and beams, then it will be easy for me to ascertain whether this particular frame is swaying or non-swaying. Okay, so let us calculate how to calculate this delta naught by VU, which is called as lateral flexibility. So before that, quickly, we also have some charts that are developed in your IS 456. These are called as alignment charts. In figure 26 and figure 27 of the code, they give these charts for determining the effective length ratios of a braced column and unbraced column respectively. Figure 26 is for braced column and figure 27 is for unbraced column. Again, how do you distinguish whether braced or unbraced? By calculating stability index. Again, for using stability index, what is that we need? We need to find that lateral flexibility, which we will discuss. Let's assume that I have found that whether the column is part of braced or unbraced. Then how to calculate the effective length? One approach is using this alignment charts. And to use these charts, first we need to find these stiffness coefficients, beta 1 and beta 2, which basically represent the degrees of rotational freedom at the top and bottom ends of the column. So whether it is how much the top and bottom supports of the column can rotate is what it is given by this beta factor. So again, beta factor, how they are determined? If you look at one joint, okay, it is, let's say, for a braced condition, okay, it is nothing but summation of your moment of inertia of all the columns that are connecting. So if I'm taking a top joint, I may have column above and below. So I calculate the moment of inertia by height of these columns. I sum them up. That is your top numerator. And the bottom, again, I add IC by HS, same value. In addition to that, I also need to calculate what is the moment of inertia by L of the beams that are connecting the joint. Now you find that here my coefficient that I have taken is 0.5 for a braced column. Same thing. Okay. So again we said, let's say this is the column and I have like this. Okay. So let's say this is the column. So if I'm doing at this joint and this joint, now I can have beams here and here. Similarly, at this joint, I can have column below and column up. So I need to calculate this beta factor at top. Let's say beta 1 here, and this is beta 2. So I need to calculate this beta 1 and beta 2 for each column, and then I have to. Now, the same column, if it is unbraced, you will find that the stiffness of the column that is top and bottom for a particular joint still remains same. Now, only thing what you see here, the denominator for beams, you put a higher value of 1.5. This is because when the column and beam in an unbraced frame, when it is bending, when it is in a braced condition, the beams are going to bend in a single curvature. In an unbraced case, the beams are going to bend in double curvature. Double curvature means you will have slope change. Okay, so just like a fixed column, that what we have said. Okay, so let's say this is a fixed case. How was this deflecting? So let's say we go back. How was this deflecting? It is deflecting like this, right? So you have a point of inflection here, point of inflection. So if you have 2 points of inflection, that means between the length of the member, it is actually bending in double curvature. So in case of an unbraced frame, your beams are going to bend in double curvature. Whenever the member is bending in double curvature, it will resist more moment, or the stiffness is going to be higher. So to account for that, here we are taking 1.5. Anyway, so if I erase this, okay. So again, the notation joint notes that the summation is for the members framing into the top joint for beta 1, and for bottom joint it is beta 2. And here increased beam stiffness is considered for unbraced columns compared to that of braced columns. Why? It is because in the braced case the beams bend in single curvature, whereas in unbraced case the beams bend in double curvature. Whenever member bends in double curvature, it is going to have higher stiffness. Okay, so that is the reason that we are accounting for that higher value of 1.5 in case of an unbraced case. Now, this is for braced condition. Again, let's look at this case. Now, again, what is braced and unbraced? Sway and non-sway is determined from Q value, or if you have a lot of shear wall, which is connecting to that moment resting frame, then you will approach this kind of a braced condition. Now, if you look at this chart, I calculate beta 1, right? And then I calculate beta 2, right? So you see here, you have different boundary conditions. Now, beta 1 can be hinged. So when can you have beta 1 hinged? Let's say if I take this column, and let's say I have only slab, no beams. Okay, so like a flat slab condition, I have only slab. In this case, I have beams. So at the top, then you will find that this will approach more or less like a hinge condition. But if you have a heavy beams that are connecting here, let's say that beam is very uh, deep beams. Okay, then this joint will approach fixed condition. However, if I don't have no beams, okay, then this joint will approach hinged condition. So it all depends upon what is the stiffness of the members that are connecting at that joint. Okay, so you can have a hinged condition at one end, and you can have fixed, or you can have both sides. Let's say in this case, if I, here also if I don't have beams, it will approach hinge condition. Here also, if I'm having very stiff beams that are framing, okay, then this will approach fixed condition. So I can have a column beta 1, either one end can be fixed or hinged, the others. So if you look at, let's take a simple case. If I am having, let's say beta 1 is approaching hinge, beta 2 is also approaching hinge. So what happens to the effective length? And here, remember, we are now here in braced condition, which is not allowed to sway. So I am taking beta 1, I am taking a value equal to 1, and beta 2 equal to 1. So here I go, here I go. So I get this value. So again, what is that value? K value. This is your K value. K value approaches 1. You see, if you go back for a braced condition for a column which is pinned, we find that K is equal to 1. That is what we have. Now, if I say another extreme condition, for a braced condition, now I'm saying that the joints are very rigid. I have very stiff beams that are connecting at the joint. Then it will approach fixity. So you will have beta will become 0 and here beta will become 0. So then what happens to the K value? K value becomes 0.5. K value becomes 0.5. So that is the effective length factor for a fixed column which is restrained to sway. So you can see here the minimum value of K for a sway condition is 0.5, the maximum value is 1. So that is what we have seen in theoretical. So these charts are very easy to use. Quickly you can find out what is your K factor. Right? Most, let's say for 0.5 and 0.5, you will find that let's say 0.5 come here and 0.5 come here. Then you will approach that, you get somewhere K value equal to 0.675. Okay. So depending upon what beta 1 and beta 2 that you have, you can find your K values like this. So we also have, so this is what we said. Let me, right. So you can have pinned condition or you can have fixed condition. So that is what we have. So for fixed condition, K is equal to 0.5. For pin condition, K is equal to 1. Similarly, I can do that for sway condition also. So sway condition is this. We have seen that when you do not have very stiff members, when the lateral flexibility is very large, then Q value becomes more than 0.05, then the frame becomes unbraced or a sway frame. So this case also, I am calculate beta 1 and I calculate beta 2. Now you can see that again, depending upon your boundary conditions, either I can have a fixed condition or I can have a hinge condition. So again, if you look at hinge condition, 1 1, if I go and my K value becomes infinity. So that is your stick which is free to rotate, right? And it is not a stable configuration, it's an unstable configuration, right? Similarly, if your beta value becomes 0 on 0, you will find that the K value is 1.01. So we saw 1. So for a unbraced condition, K values between 1 and infinity. So that is what we saw. So that is what these charts are also, the values are given here, right? So in this way, we can calculate your things. So this is what we have discussed previously also. In this case, pin to pin, LE becomes infinity. For fixed, LE becomes equal to unsupported length. Right. So the same kind of things are again expressed in the form of equations also. Now, again, for top and bottom joint of a column, I calculate the stiffness parameters alpha 1 and alpha 2, which is basically summation of your stiffness of the columns divided by summation of the stiffness of the beams that are connecting at the top of the column. Okay. Similarly, I do that for bottom of the column. So basically, these alpha 1 and alpha 2 are nothing but stiffness parameters of the boundary conditions of the columns. So for this, now K value can be expressed in terms of alpha 1 and alpha 2 that I am calculating based on the stiffness of the columns and beams that are connecting at that particular joint. So you can see if you calculate alpha 1 and alpha 2, I can plug into this equation, find what is the value for your K. Okay. So similarly, this is for a braced column and this for an unbraced column. So like this, we can find K using this equation. So first step is to find whether the column is braced or unbraced. The moment we know that, either I can go ahead and use alignment charts to find the K value, or I can use these equations to find what is the K value. So that is a thing. So the moment K value is calculated, you know effective length, then effective length by the least lateral dimension for the axis that you're considering, then you can calculate the slenderness. So why we are doing all these things? Our idea is to calculate the slenderness ratio. To calculate the slenderness ratio, I need to know what is the effective length. To know the effective length, I need to know whether the column is part of the braced frame or an unbraced frame. So to distinguish that, I need to calculate again stability index, then go ahead and find the K factor to calculate your effective length, right?